Okay, so this is day 5 of prep chemistry, and today we're finally going to talk about chemical bonds, which is super exciting. But first, we're going to quickly review some stuff from the last couple days that's going to be important for figuring out how those bonds are going to form. So yesterday, we talked about valence electrons. So if you need more practice on that, I recommend you go watch the day 4 video. So the process for figuring out how many valence electrons a given atom will have is for a neutral atom, the number of total electrons is equal to the number of protons, which is the atomic number. So this we talked about a lot on day 3. So you can get the atomic number from the periodic table, or it would be given to you. And if the charge is 0, the number of negatively charged electrons has to be equal to the number of positively charged protons. So that lets us count our total number of electrons that we have. And then we fill our orbitals from the lowest energy level to the highest. And in a given sublevel, every orbital has to get 1 electron before any orbital gets a second one. And then valence electrons are the electrons in the highest energy level that has any electrons at all. And again, we're just talking about those core group, those main group elements, not the transition metals right now. So if we have an element with 1 proton, that would be hydrogen. It would have 1 electron, and that electron would go in the 1s orbital. And then our first energy level is the highest energy level that has any electrons in it, so it has 1 valence electron. Helium has 2 protons and therefore 2 electrons. And so it gets a second electron in that 1s orbital. Now the 1s orbital is full. So when we move on to when we move on to lithium, which has 3 protons and therefore 3 electrons, we need to move into our 2s orbital. So now our second energy level is our valence shell. Lithium has 1 valence electron and 2 core electrons. So core electrons are whatever electrons are not valence electrons. Okay. Then if we move on to beryllium, it has 4 protons, 4 electrons, so 2 valence electrons, 2 core electrons. Then boron, and so on and so forth. So this is boron, carbon, nitrogen, oxygen, fluorine, neon. So neon now has this full valence shell, which we're going to talk about today. Whenever you have a full valence shell, that atom is really stable. So then when we add 1 more electron, we move on to sodium. And now our third energy level is our valence shell. So sodium has 1 valence electron and 10 core electrons for a total of 11 electrons. And so we can keep filling. And now this is argon, which has a full 3rd level valence shell. So does anybody have any questions on how to count valence electrons? You guys did a really good job on this on the problem sets that were submitted. So I think people are generally feeling okay about it. But counting those valence electrons is going to be really important.
I have a question about core electrons.
Yep.
So is any electron that's not a valence electron a core electron?
Exactly.
Okay, thank you.
So the number of total electrons that you count in step 1 should be the total, the sum of your valence electrons plus your core electrons. So if you know the total number of electrons and you know the number of valence electrons, you just subtract them. Good question. Okay. So, oh yeah, go ahead.
I have a question about valence electrons. So you said that if there's 8 valence electrons, then it is a really stable element. But does that mean the opposite is true? Like if there's 1 valence electron, then it's extremely unstable, or is it different than that?
So that's going to be the whole thing we're going to talk about today. But basically, atoms are going to try to do something to end up with a full valence shell. So if it already has a full valence shell, it doesn't need to do anything. So it's not going to do any reactions or form any bonds or whatever. It's happy as it is. If it doesn't have a full valence shell, then it's going to try to react. It's going to try to find a friend and do something to fill up its valence shell. But that's going to be like the whole focus of today is basically what are atoms going to do to try to end up with a full valence shell. So that's a great question. The method that we just used for counting valence electrons is really great for these first few rows where you only have, 20 electrons or whatever. It's really annoying to go like draw a million energy levels to figure out how many valence electrons, cesium has. So we can use this trick that each vertical column in the periodic table has the same number of valence electrons. So anybody in this first column has 1 valence electron. So we counted for lithium how many valence electrons it has and how many valence electrons sodium has by filling up those shells. But we can also just find it on the periodic table and look at what column it's in. So this second column has 2 valence electrons, and then we skip over the transition metals. So then we just keep counting. So this column that has boron in it has 3, then 4, 5, 6, 7. So this 8th column, these guys all have 8 valence electrons. Helium, like we talked about, only has 2 because it's only filling that first level. So it only has 2 valence electrons, but it has a full valence shell because its valence shell is the first level, and the first level only has room for 2 electrons. So it only has 2 valence electrons, but it's acting like all of these other ones because it has a full valence shell, just like neon or argon or krypton. Does this make sense? So if I asked you, like, how many valence electrons does, bromine have? Bromine's way down here. It has 7. You don't need to fill up all those shells. So it's useful to know how to fill up those orbitals and in what order they get filled up in. But you can just read the number of valence electrons off the periodic table. Questions on that? Okay. So the last thing we talked about yesterday is Lewis structures, sometimes called Lewis dot structures or Lewis dot diagrams. They help us visualize how full our valence shell is. So if an atom had 1 valence electron, we would draw it like this: 2, 3, 4, 5, 6, 7, 8. And like somebody was just asking about, atoms want to have a full valence shell. They're very stable if they have a full valence shell. So this last column that we were just talking about, all of those atoms, all of those elements have a full valence shell without needing any help from anybody else. So argon, for example, is right here. We would draw its Lewis structure like this, and it has a full valence shell. We call these noble gases because they're very stable. They don't do anything. There's no drama. They're very calm and collected. They just hang out. They don't react with anybody for the most part. So helium is kind of a weird exception. I led you astray on this one a little bit yesterday. So helium has a full valence shell. It has 2 valence electrons, but we draw them together like 2 dots like this, just to kind of indicate to us that it's happy like that, it's full. But most of the noble gases, well, all of the other noble gases have 8. Does this make sense? Okay. So going back to that question about what happens when we don't have a full valence shell. Compounds are multiple kinds of atoms bonded together. So this forms the basis of like every cell in your body, like most chemicals that you come across in life have, different kinds of atoms bonded together. So why does this happen? It happens because atoms want to have a full valence shell. So carbon has 4 valence electrons. We've counted that before. And so when it has no bonds, it's not very happy. It only has 4 valence electrons. Its valence shell has room for 8. It really wants those 8 valence electrons, right? So it wants to look like this, but it can't just like materialize electrons out of thin air. Hydrogen has 1 valence electron, and because its first energy level is its valence shell, it wants 2 valence electrons. So hydrogen has 1 valence electron and it wants 2. And carbon has 4 valence electrons and it wants 8. So they can a carbon and a hydrogen atom can kind of find each other and be like, look, we both want more electrons. If you let me hold on to your electrons, I'll let you hold on to mine. And then we've all got more electrons. We're sharing, everybody's happy. So that's what happens is we had 4 hydrogen atoms that each have 1 electron, and we have 1 carbon atom that has 4 electrons. So that's 4 valence electrons. So that's 8 valence electrons total, and now everybody's happy. Carbon has 8 electrons around it, and each of these hydrogen atoms has 2 electrons. So this is a happy molecule. Does anybody have any questions about like why this happened or who's happy, who's unhappy?
I kind of have a question with like helium.
Okay.
So since helium has 2 valence electrons, but technically it acts like a noble gas because its shell is full, could it still pair up with other atoms?
There are some really weird, really short-lived helium compounds, but pretty much no. You can think of it as like, no, its valence shell is full, it's happy, it's not really gonna bond with anybody else. So we can force it to by doing weird stuff, but in general, it's not gonna bond with anybody else. So and that's true of all of the noble gases. Once its valence shell is full, it's happy. So for helium, that means 2 electrons because its first level is the valence shell. And then for all the higher ones like neon and argon, its valence shell has room for 8 and it has 8 and they're happy. So all of the like bonding we're going to talk about is never going to involve those noble gases because they don't need to share with anybody. They've got everything they need right there. Okay, so just to reiterate, because I'm going to make you practice in a minute, a carbon atom has 4 valence electrons and it wants 8. So it needs 4 more. So it needs to it needs to share electrons with 4 different other atoms. Hydrogen has 1 valence electron and it wants 2. So a given hydrogen atom only needs to form 1 bond in order to be happy. So this carbon atom has 4 bonds with 4 different hydrogen atoms. Because it had 4 valence electrons, it wants 8, so it wants to make 4 bonds to fill up its valence shell. Each of these hydrogen atoms only makes 1 bond because it only needs 1 more valence electron to be happy. Any questions on this? Okay. So as an example, we're going to practice with oxygen. So oxygen has an atomic number of 8 and a mass number of 16. So the steps that we're going to follow, how many protons does oxygen have? That will tell us how many electrons it has if it's neutral. Then we can count how many valence electrons it has, either by filling up our orbitals or by looking at what column it's in on the periodic table. Then we can draw its Lewis structure, and we can figure out from how many valence electrons it has, or from looking at its Lewis structure, how many bonds it wants to form. Okay? So I'm going to sort you into breakout rooms to practice with this. I'll give you 5 or 6 minutes. So I'll pull you back at like 11:02. So you should have just gotten an invite to breakout. So go ahead and accept those. And then I'm going to pause the recording. But if you're watching this later, pause the video and practice. Okay, welcome back. I'll just give it a minute for people to cycle back in. Okay, welcome back. So just to see how this went, I'm going to launch a poll asking the last question here. So how many bonds does oxygen want to form? Cool, looking good so far. Okay, so about 85 to 90% of you said 2, which is correct. So I'm gonna go through how we get there, and then those of you who didn't say 2 or weren't sure, let me know at that point if it's still not clear. So oxygen has an atomic number of, yeah, go ahead. Okay. If there's a question, speak up. Yeah. Okay. So oxygen has an atomic number of 8. So that means by definition, it has 8 protons. For a neutral atom, if it has 8 protons, it needs to have 8 electrons. So then for the valence electrons, we can either fill up all the shells. And so the first level would have 2 electrons, and then we would fill in the second level and it would have 6. Or we can look at the columns on the periodic table and see that it's in the column that has 6 valence electrons. So once you have that, you can draw the Lewis structure of oxygen, where we have 1, 2, 3, 4, 5, 6 valence electrons, where 2 of those are alone and sad and unpaired and want to make a friend. So that means that oxygen wants to form 2 bonds because it has 2 empty holes in its little heart that it wants to fill with friends. So it wants to form 2 bonds, and that's where we get H2O, or water, is that it can form those bonds with all sorts of stuff, but when it forms them with hydrogen, we get H2O, or water. So anybody have any questions on this? Yeah.
For the oxygen thing, can it like bond with another this element that has two valence electrons, you know? Like,
So it wants to form two bonds. We will talk about the kind of bonds that you're talking about a little bit later today. So kind of, yes, but we're not there yet. So hold tight. But yeah.
okay, yeah.
And it can form these bonds with carbon or, you know, all sorts of other elements. So this, what I'm drawing here of H2O is just an example. But for now, just realize that oxygen wants to form two bonds. Okay, so we're gonna have all sorts of compounds that are combinations of various different kinds of atoms. And we kind of need to agree on how we're gonna draw them. So here's an example of this molecule is called methanol. You don't have to worry for now about why it's called methanol. This is methanol, trust me. And so methanol has carbon with 4 bonds. So it has 1, 2, 3, 4 bonds. So it has a full valence shell. And then oxygen has 2 bonds. It has 1 bond with carbon and 1 bond with hydrogen. So it's happy, it has a full valence shell. And then all of these hydrogen atoms have 1 bond each. They have 2 valence electrons. For them, that's a full valence shell, so they're happy. This is methanol. It gets pretty annoying to draw these dots over and over and over again. So as shorthand, we just draw a line. So any line is 1 single bond, and a line means 2 electrons shared. So a single bond is a single line, and that signifies 2 electrons being shared. So these 2 things I've drawn here are the same thing. These are both methanol. If we don't care so much about seeing all of the bonds, we can just write out all of the atoms that are involved here. So we have a carbon, which is bonded to 3 different hydrogens, and then an oxygen, which is bonded to its own hydrogen. It also gets annoying to write down HHH. And so we write this as CH3OH. So that lowercase or that subscript 3 means there's 3 hydrogens in a row that I'm just not bothering to write out. So I'm just going to pause here for a second. All 3 of these things that I've drawn here mean the same thing. So CH3OH represents this, which also represents this. These all represent the same compound. So when we have more complicated examples, so again, don't worry about the naming right now, but this compound is called 2-chlorobutane. So it has 4 carbons, a bunch of hydrogens, and 1 chlorine here. So again, each of these carbons has 4 bonds. If you ever see a carbon, if you ever are drawing something and find that you have a carbon that doesn't have 4 bonds, something is wrong, probably. Each of these hydrogens has 1 bond. If you ever are drawing something and hydrogen has more than 1 bond, something is wrong, most likely. So if we write this as CH3, so that first carbon has 3 hydrogens. The second carbon has a hydrogen and a chlorine. The third carbon has 2 hydrogens. And the last carbon has 3 hydrogens. So this way that I've written this represents this same molecule. I can also just count total. It has 4 carbons, 9 hydrogens, and 1 chlorine. So I could write it as CH4H9Cl. That would represent the same thing. So this is fine, it's not wrong, but just realize that you've lost a little bit of information because now I don't really know where this chlorine is. It could be on the end, it could be anywhere. So this is fine, but writing it this way just conveys a little bit more information. Any questions about drawing these bonds or counting these atoms? So if I look at the way that I've written it right here, I have 3 hydrogens, 4, 5, 6, 7, 8, 9. So you always use those subscript 3s or 2s or whatever to figure out how many of a given element you have. When I shortened it to C4H9Cl, does it matter in which order they're written? There are conventions about what order it's written in, so it would be really unusual to see it written as H9Cl C4, and there are rules about, figuring out which order to write them in, but it does convey the same information. So for now, I wouldn't worry about those rules. If you write H9C4Cl on your homework, that's fine. The most important thing right now is just keeping track of the total number of each type of atom involved. But yeah, we normally write the carbons first. Yeah, there's a hand.
I was gonna say, isn't it when you write it out, the correct way to do it is in the order of the periodic table?
No, because hydrogen would come first in that case.
Oh, okay.
Yeah, so I wouldn't worry too much about the order of these for now. I would just keep track of how many of each element we have. That's the most important thing for right now. Okay. So the last one I want to talk about before we kind of go summarize what we've done so far is we just talked about how oxygen is unhappy, right? It has 6 valence electrons and it wants 8. So it is happy to form 2 bonds with 2 other things, so like H2O, or it can form a double bond with another atom. So in this case, it's forming a double bond with another oxygen atom. So when you have oxygen, the oxygen you breathe is not in this form. It's not one single oxygen atom floating around, because that is unstable. It's not happy. It wants to fill that valence shell. The oxygen that's floating around in the air and makes up the air is in this form. So this thing here, instead of sharing 2 electrons, it's sharing 4. And so that is a double bond. And so we draw a double bond as 2 lines. So each line always signifies 2 electrons. So this double line signifies 4 electrons. And then these pairs of electrons that were already happy, they didn't need to form any bonds, we call those lone pairs. There are pairs of electrons that are just sitting on an atom. They're not involved in any bonds. Does this make sense? Anybody have any questions? So a single bond is 1 line. It means 2 electrons. A double bond is 2 lines. It means 2 electrons. Okay, so just to summarize what we've talked about so far, atoms want a full valence shell. For hydrogen and helium, that means 2 valence electrons. For everybody else, it means 8. Again, within the main group, we're not really talking about transition metals. They share electrons with other atoms in order to fill their valence shell. So everybody wants a full valence shell, and so they find a friend to share with so that everybody's valence shell can be full. If they're sharing 2 electrons, that's a bond. If they're sharing 4 electrons, that's a double bond. And we haven't seen an example of this yet, but by exactly the same logic, Sometimes they can share 6 electrons, which would be a triple bond. And so when we're writing this down, if we have multiples of the same element, we can write a subscript. So one example you had on your homework a couple days ago is a carbon atom and 4 fluorine atoms make CF4. And so instead of writing CFFF, we've written CF4. Questions so far? Okay. So I want to talk just a little bit about the shapes of molecules. This is like a whole complicated thing. So I don't want to try to figure out the shape of every molecule that's ever going to exist. But when I have this carbon atom with 4 hydrogen atoms, in general, these want to be spaced out as far away from each other as they can be. So it's going to form this shape shown here. So the way that I think about this is if my CH4 atom was totally flat, kind of like I've drawn it here, there would be a 90-degree angle between each hydrogen atom. But if I let it sort of bend here, there is bigger than 90 degrees between each hydrogen atom, so it's happier. So I don't want you to panic about like trying to figure out the shape of all kinds of molecules, but just realize that when we draw them flat on paper, that's not actually how they float around in real life. And these bonds are going to bend. And again, just so you've seen it before, don't like panic about trying to memorize this. We can draw this type of 3-dimensional shape on the left like this, where bonds that are coming out of the page towards us have this little triangle, and bonds that are going back away, like into the screen, have these dashes. So don't worry about this too much. Again, I just kind of want you to realize that these molecules are 3-dimensional, even though we're drawing them 2-dimensional on the page. So just as another example, this is H2O, and it's actually going to be bent. So you might think it's going to go HOH in a straight line, but it's actually going to be bent because these lone pairs, these free electron pairs, actually kind of take up space. And so they push those hydrogen atoms away. So again, the takeaway here is just that bonds can bend and those lone pairs take up space and affect the shape of molecules. Does anybody have any questions on this? We could spend weeks on what is the shape of all sorts of various compounds, but I just kind of want to give you a taste that they're not flat. Does that make sense? Any questions? So there's yet more simplified ways of drawing our line drawings. So we know that always carbon is going to want 4 bonds and hydrogen is going to want 1. So, and those carbon-hydrogen bonds are really, really common. So this is that same 2-chlorobutane molecule that we showed on a previous slide. So we can simplify the way we've drawn this to draw it like this. And so I'm going to walk through this step by step. But basically the point of this is there's so many carbon-hydrogen bonds that we can kind of just leave the hydrogens off of there and not draw them because we know they must be there. So because carbon is one of our most common elements, we just don't write the C. So anytime we've drawn a bond and it ends without what element specified, that element is carbon. So these ends of these bonds are our 4 carbon atoms that are represented over here. We've drawn a bond ending in chlorine where we've actually written out the Cl because it's not carbon. So if we write out what element it is, it's chlorine. If we don't write what element it is, but we draw the bond, it's carbon. And then the last thing is, yeah, go ahead.
Is it always carbon, right?
It's always carbon. If we draw a bond and don't specify what it ends in, it's carbon. Because if it was anything else, we would write it out. So here it ends in not carbon, so we've written out the chlorine. So anywhere where we didn't write a letter where the bond ends, it's always carbon. So yeah, not just in this example, in any molecule, if we don't write out what the element is, it's carbon. And then we also know that carbon wants 4 bonds. And so wherever we have drawn a carbon without 4 bonds, the extra missing bonds are bonds with hydrogen. So in this case, we have a carbon right here. We've drawn 1 bond, and we know it needs 3 more. So there must be 3 hydrogens bonded to this carbon. Right here, we have a carbon where we've drawn 3 bonds coming off of it. It must have a 4th bond, so it needs 1 more hydrogen. That's this hydrogen right here. This carbon, we've drawn 2 bonds. It needs 2 more, so it must have 2 hydrogens. That's these 2 hydrogens right here. And then our last carbon on the end needs 3 more bonds. So those 3 bonds are hydrogen, and those are these 3 hydrogens right here. So these 2 drawings on the left and the right are representing the same molecule. We're just sort of by shorthand leaving off the parts that we know must be there. So just to say it again, if we have a bond that we've drawn the bond and it ends without us specifying what element it is, it's carbon. If we haven't drawn a bond at all, but we know there must be one there in order for carbon to have enough bonds, the extra bonds are hydrogen. And then for any other atom, like the chlorine right here, we just draw it like we would have before. Does this make sense? I know this is really confusing. I remember being really confused by this the first time.
So if it's not like if it's nothing there and it's carbon, it'll always be, you basically like add up how many carbons it needs to be, neutral or hydrogen, sorry.
Hydrogens, yep, exactly. So you figure out for each carbon atom, how many extra bonds does it need in order to be happy? And those extra bonds are going to be hydrogen. So wherever you have a carbon that has less than 4 bonds, it must have enough extra bonds with hydrogen to make up for that.
And it's always hydrogen, right?
Yep. If it was anything else, it can have bonds with things that are not hydrogen, but we would write it. So in this case, this carbon has a bond with a chlorine, so we've written that chlorine. So if that carbon had a bond with anything other than hydrogen, we would have actually drawn the bond and written what it's bonded to. So if we haven't drawn it, it's hydrogen. Thank you for asking. Those are good clarifications. So the reason that I remember first learning this and thinking, it's not that hard to draw this thing on the left. And when I draw the thing on the right, it's so much more complicated. Like I have to remember that these are carbons. I have to count how many hydrogens there are. And 2 things. First of all, as you look at more and more of these compounds, that will get more and more automatic for you. It'll be, you'll look at this and not have to count. You'll just get used to seeing it. And that will just happen over time. But also, when you get to studying really, really complicated molecules like this one, so this is testosterone, there's a lot going on here, right? There's so many bonds. And if I tried to draw all of the hydrogens coming off of all of these carbons, it would be so busy and so hard to process what's going on here. So here's a great example. I'm not going to take the time to do it right now, but if you want to practice at home, you can count the carbons and hydrogens here, and you should get the same number I have here. So the carbons are anywhere that there's a bond ending without us specifying what it is. So 1, 2, 3, 4, 5, 6, 7, 8, etc. So this might be a good challenge molecule to practice with. And it also has some double bonds. So this carbon down here has 1, 2, 3 bonds coming off of it. That double bond counts as 2 bonds. So this carbon down here only needs 1 more bond. It needs that 1 more bond with hydrogen. So does this make sense? I'm going to pause for questions because I'm going to make you practice in a minute. Awesome. I saw some thumbs up. Cool. So this molecule is called benzene. And I want you to count how many atoms benzene has and how many of each are there. So how many carbons are there? How many hydrogens are there? Are there any oxygens, etc.? And then given that, what's the chemical formula? So with those subscripts, and then count the bonds, how many double bonds and how many single bonds. So for now, for practice for yourself, you might want to start by redrawing it, but drawing all of the letters and all of the bonds. Or if you feel really comfortable not doing that, you don't have to, but that can be a good sort of trick, is to redraw it with all the bonds and then count from there. Does anybody have any questions on like the rules or how to do this? Okay. I'm going to send you into the breakout rooms. I'll give you, I don't know, 6 minutes or so. So I'll pull you back at like 11:33-ish. Okay, so go ahead and accept those breakout room invitations if you haven't already. For the sake of future recordings, I'm going to pause the video now. You might want to pause it too to practice. Okay, I think everybody's back. Just to see how we did, I just launched a poll that's just asking how many carbons does benzene have and how many hydrogens does benzene have. So go ahead and answer that. Okay, looking good so far. I'll give you about 20 more seconds to answer. Okay, so about 90% of you think that benzene has 6 carbons, And about 75% of you think that benzene has 6 hydrogens. So that majority is correct, but we're going to go through how we get there. So when I was first starting to do this, I think often the easiest way is to just redraw the molecule. So we have the bonds that are actually shown always end in carbon. So that means there's carbons at all of these corners. And then each of those carbons needs to have 4 total bonds. What's shown is 3 total bonds, 1, 2, 3. So it needs a 4th bond, which is going to be hydrogen. And so that's true of all 6 of the carbons, have 3 bonds shown, and they need 1 more, their 4th hydrogen. So then when you draw it out like this, you can see that there are 6 carbons. Those are where the bonds end without us specifying what kind of bond it is. And then 6 hydrogens, where those 6 carbons each need 1 more friend. Questions on that? Okay, so then we can just use our subscripts to write it out. So we can write C6H6. Again, you could write CHCHCH, CHCHCH, but that would be annoying for you to have to write that out. So we can just write it out as C6H6. And then when we actually go count the bonds, we can see 3 double bonds right here. And then 1, 2, 3 single bonds between the carbons, and then 6 more single bonds between the CH. Any questions on how I did this? You'll have lots of practice on the homework. I see a hand.
Wait, so how does carbon create a double bond?
In exactly the same way as oxygen does. So the carbon has 4. It's a little hard to, okay, I'll try it this way. So my carbon has 4 valence electrons, right? And so it can sit next to another carbon atom and share that 1 valence electron and go like this. Or they can each put in another one of their valence electrons and form a second bond. So then you'd have the carbon with 2 valence electrons left over and a double bond like this. And so each of them now have 1, 2, 3, 4, 5, 6 valence electrons, and they still need 2 more bonds. So they can bond with, let's say, another hydrogen and another carbon. Does that make sense?
Yeah, it does. Thank you.
Okay. So it would take me like 5 minutes to draw with my mouse all of the dots, but I can, if that's still unclear, I can send it out or something. Okay. Cool. So the last thing I want to talk about today is ions. So ions are things that don't have a 0 charge. So we've been talking about if an atom is neutral, it has to have the same number of protons and neutrons, or sorry, protons and electrons. But not everything is always neutral. So this is sodium. This is the Lewis structure of sodium. It has 1 valence electron. So you can figure that out either by filling up all the orbitals or by finding the column on the periodic table. So sodium has one valence electron. It is not going to make 7 bonds. First of all, because there's not room, like it doesn't have space for 7 different people to be near it, but also it would need to share. Like nobody wants to bond with you if you don't have an electron to share with them. So instead, what sodium's going to do to end up with a full valence shell is it's actually going to get rid of this electron. It's going to give that electron away to somebody else. And then that electron was in its 3rd level. It was the only electron in that 3rd level. And so now, once it gets rid of that electron, there's no more electrons in that 3rd level. So now the 2nd level is its valence shell. So now it has a full valence shell, but it has a +1 charge because it lost an electron. An electron has a -1 charge. And so if you lose an electron, you end up with now 1 more proton than electrons, and you have a +1 charge. Does anybody have any questions on how this happened? We'll talk in a second about where that electron goes, but for now, just think of it as it has given it away to somebody else. And it's now, it used to have 1 electron in the 3rd valence shell, so it had 1 valence electron, but now it gave away its only 3rd level electron. So now the 3rd level is empty. It has a full 2nd level still, and its 2nd level is now the valence shell because there's none in the 3rd level. And so it has a full valence shell. It is now happy, but it has a +1 charge. Okay. So chlorine has 7 valence electrons. You can find that out again, either by filling up those orbitals like we did on the first slide today or all day yesterday, or you can just find what column it's in the periodic table. So it has 7 valence electrons. It wants 8. So it can either form a bond with like carbon, like it did on the previous slide, and form sort of a normal covalent bond to share, or it can steal an electron from somebody else, gain 1 extra electron, and now it has more electrons than protons, so it has a -1 charge. So it now has a full valence shell because it stole an electron from somebody else. Does anyone have questions on either of these? So maybe you can start to see that these guys can also make a deal. Sodium has this extra electron that it doesn't really want. It would love to get rid of it and just have a full 2nd level valence shell. Chlorine only needs 1 more electron to be happy. So it's perfectly happy to do sodium a favor and take that extra electron. And now one of them will be a positive charge and the chlorine will be a negative charge. And then the last thing you need to know about these ions is that they want to exist in groups that have a net total of 0 charge. And that's in part because of these electrons. Sodium wants to lose 1 electron, chlorine wants to gain 1 electron. And so 1 sodium will happily hang out with 1 chlorine. But if we instead had somebody with a +2 charge, so let's say beryllium has a +2 charge, it has 2 valence electrons, it wants to get rid of 2 electrons, then it would need 2 different chlorines that can each only accept 1. So you'd have 1 beryllium hanging out with 2 different chlorines. Does this make sense? So we need the total charge to be 0. So in this case, sodium is +1, chlorine is -1. They're perfectly happy to just hang out together. So this shows us that there are two different kinds of bonds. The first kind that we talked about today is called a covalent bond. Now, you might have heard that word before and maybe memorized what it means, but now you know where it comes from because it's co, kind of means sharing or together, and valent means valence electrons. So covalent, these two atoms are sharing their valence shell. Those valence shells are kind of joining together. So carbon and hydrogen both want more electrons than they have, so they share so that they each have enough. Ionic bonds are the ones we just talked about that involve ions, which are things with charge. And so sodium wants fewer electrons, chlorine wants more electrons, so one steals an electron from the other. Sodium now has a full valence shell, chlorine now also has a full valence shell, and it's called electrostatics, when things that are charged are attracted to each other and hang out. So sodium and chlorine are going to hang out together because one's positive and one's negative, and that makes them happy. Questions about covalent versus ionic bonds? So in the same way that we know how many valence electrons an atom has based on where it is on the periodic table, for that exact same reason, we can tell what charge it's going to have. So anybody that has one valence electron wants to get rid of it, and then they'll have fewer electrons and they'll end up with a +1 charge. So this whole column right here is going to want to end up with a +1 charge. And I don't like memorizing words, but just so you've heard it before, these are called the alkali metals. This whole column has two valence electrons. So if they want to form an ion, they're going to get rid of those two valence electrons and end up with a +2 charge because they've lost two of their negatively charged electrons. We call those the alkaline earth metals. These guys over here that have 7 valence electrons, they want to gain one more and therefore end up with a -1 charge. So those are called the halogens. Again, don't memorize those words, but just so you've heard them before and know what they mean. And then the last thing here is these noble gases. They don't want to gain or lose any electrons. They already have their happy full valence shell. So they're not going to form ions. They're going to keep their charge of 0, and they don't need any help from anybody. Questions on this? Okay. So using that as practice, what do you think is the most likely charge of an ion formed from the elements that I've boxed here? So calcium, iodine, and neon. I'll give you a minute to think about it, and then I'll send out a poll. I just launched the poll. I'll give you about a minute to think about it and answer the poll. So just as a reminder, you can use the columns on the periodic table to figure out how many valence electrons a given atom wants to have, or a given atom does have, and you know it wants a full valence shell, and that will determine what charge it's going to have. Awesome. You guys are doing great. Okay. So about 80% of you said that an ion of calcium would have a +2 charge, and that's right. So calcium, you can tell from what column it's in, it has 2 valence electrons. If it gets rid of 2 electrons, it's gotten rid of 2 negatively charged things. So now it's going to have a charge of +2. So it's a little confusing because it's lost electrons, but it's kind of a double negative because it's lost things that are negative. So that calcium is going to have a +2 charge. So next is iodine. It has 7 valence electrons. It's going to take 1 more to end up with 8. And if you gain a negatively charged thing, you end up with a charge of -1. And then the last thing is neon. About 91% of you said that neon would have a charge of 0, and you're right. It's already happy. It's a noble gas. Its valence shell is already totally full. So it is not going to make an ion. It's not going to gain or lose electrons because it's already happy. Any questions on how I did this? Okay, so the last thing that we talked about on the previous slide is that atoms that are charged want to hang out with other atoms in such a way that they will have a total of 0 charge. So if one atom of calcium, which is +2, hangs out with one atom of iodine, which is -1, +2 plus -1 is still +1. So it's still charged and it wants a charge of 0. So it's going to hang out with a second iodine atom to end up with +2 from the calcium and 2 different -1s from the 2 different iodine atoms. So we're going to have calcium and 2 iodine atoms. And just as a reminder, so calcium had 2 valence electrons, and it wants to get rid of them. It wants to have a full valence shell, so it's going to get rid of those spare couple of electrons. If you get rid of 2 negatively charged things, you're going to end up with a more positive charge. You didn't get rid of any protons, so now you used to have the same number of protons as electrons, but now you've gotten rid of 2 electrons. So you have 2 more protons than electrons, and you're happy. So calcium has a +2 charge, iodine has a -1 charge, and they want to have, when they hang out with each other, they want to have a net 0 charge. So you're going to have 1 calcium atom with 2 iodine atoms. Does that make sense, that grouping together so that the charge is 0? I'm going to show you an example. So now we're looking at lithium and oxygen. So the first question is, what charge do you think an ion of lithium would have? And what charge would an ion of oxygen have? So we're going to just use the exact same rules as before. And so what we're seeing here is that oxygen could form covalent bonds like it did before when it was sharing with hydrogen, but it can also make an ion. So I'll give you about 30 more seconds to answer this. Okay, you guys are doing great. Gonna end the poll in about 10 seconds. Okay, so lithium has 1 valence electron. It would like to have a full valence shell, so it can either gain 7 electrons, which is really hard. You're gonna have to find 7 friends you can steal electrons from. So that's not gonna happen. So instead, it gets rid of its spare electron. It now has 2. It has a full first level and an empty second level. So its first level is now its valence shell. And when you get rid of a negative thing, you end up more positive. So lithium has a charge of +1. Oxygen has 6 valence electrons. We can tell by what column it's in. And what it's going to do is gain 2 electrons. And when you gain 2 electrons, you're now more negative than you were before. And so it has a charge of -2. So it's a little confusing because it's gaining more electrons, but those electrons are negative. So it's making its charge more negative. So you guys did great. So just to reiterate what I just said out loud, lithium has a charge of +1, oxygen has a charge of -2. When they hang out with each other, they want to have a net neutral charge. So I need 1 oxygen atom, but 2 lithium atoms, so that I have +2 from the lithium and -2 from the oxygen. So it's going to hang out in the form of Li2O, so that 2 lithiums and 1 oxygen. Any questions on that? Okay, awesome job. Homework 5 is posted. It'll be due Monday. It also includes a quick check-in, which I'll paste in the chat as well, and I'll send out via an announcement. So I'm just trying to get a feel for how things are going so far. So I'd love your feedback on just sort of how's the pace, how are the problem sets and everything like that. And stick around if you have any questions. I am happy to talk through things as always. You guys are doing an awesome job so far.